and water.
Water. Introduction. Water is an important natural resource, and all the living things on earth depend on water. Living things need water for survival and growth. Nearly 3/4 of the earth's surface is covered with water, and it is a habitat for many marine plants and animals living in various water bodies like rivers, seas, oceans, and other water bodies. Humans need about 2 to 3 liters of water every day. The blood in our body is mostly water. It is in our blood that help in absorption of nutrients and their transportation to the different parts of our body. Water helps the animals to maintain their body temperature. Amount of water present in some substances are as follows: milk, cucumber and jellyfish 95%, tomato 90%, potato 80%, meat 75%, human body 70%, fish 67%, tree 60%. Constituents of water. Water is a compound made up of 2 hydrogen atoms and 1 oxygen atom. The molecular formula of water is H2O. In the year 1781, Henry Cavendish demonstrated that water contains only hydrogen and oxygen. These elements are in the ratio of 1:8. Volumetric composition of water. The volumetric composition of water can be easily determined with the help of Hoffman's water voltmeter. It is an apparatus consisting of 2 graduated cylindrical tubes connected by a horizontal tube at the bottom. The top portions of the tubes are closed with airtight stoppers. Another vertical tube with a bulb is kept in between the tubes and is attached to the middle of the horizontal tube. The tubes are closed with rubber corks at the bottom. Through the rubber corks, platinum electrodes are introduced. Acidified water is poured into the bulb of the middle tube, keeping the stopper of graduated tubes open so that air in them can be displaced. When the graduated tubes are filled with water, the stopcocks are closed. The platinum electrodes are connected to the terminals of a battery and current is passed. Water decomposes to give the elements hydrogen and oxygen. Hydrogen is liberated at the negative electrode, cathode, and oxygen at the positive electrode, anode. When electricity is passed through water, 2H2 is deposited at cathode and O2 is deposited at anode. Properties of water. Physical properties of water. Pure water is transparent, colorless, tasteless, and odorless. Its boiling point is 100 degrees centigrade and freezing point is 0 degrees centigrade. Water exists in 3 different states: ice, water, and water vapor, that is, steam. It's a very good solvent and is called a universal solvent. Chemical properties of water. Action of water on metals. Drop a piece of sodium into a test tube containing water. Close its mouth with a 1-hole cork. Insert a jet tube into the water as shown in figure. What gas is evolved? Feel the test tube by touching its outer surface. A vigorous reaction takes place between sodium metal and water. Hydrogen is liberated. A hot solution of sodium hydroxide remains in the test tube. 2Na plus 2H2O is equal to 2NaOH plus H2. Action of water on less reaction metals. Clamp a round-bottomed flask containing some water. Cover it with a 2-hole stopper. Insert a thistle funnel through one hole and a side tube through the other. The side tube is inserted into a hard glass tube containing iron, zinc or magnesium as shown in figure. Boil the water strongly so that steam is produced steadily. The metal in the hard glass tube is simultaneously heated. The steam is passed over the red-hot metal. Light the gas coming out of the other opening of the hard glass tube. How does it burn? Hot water or steam reacts with magnesium, zinc or iron, evolving hydrogen gas. Mg plus H2O gives MgO plus H2. Zn plus H2O gives ZnO plus H2. 3Fe plus 4H2O gives Fe3O4 plus 4H2. Hard and soft water. Take 2 beakers. Number them as 1 and 2. Pour some distilled water in beaker 1 and some magnesium sulfate solution in beaker 2. Add equal volumes of soap solution to each. Shake well. What do you observe? The water in beaker 1 lathers with soap quickly, but the water in beaker 2 does not lather with soap. Instead, it forms a curdy white precipitate. Water which readily lathers with soap is known as soft water. That which does not lather readily with soap is called hard water. Advantages of using hard water. For drinking purposes, soft water is not desirable since small quantities of calcium and magnesium salts are essential for good health. Usually, water is supplied through lead pipes. Soft water dissolves lead much more readily than hard water. Therefore, there are less chances of lead poisoning with hard water than with soft water. Disadvantages of using hard water. Hard water does not lather with soap easily. It requires more soap for washing purposes. Hard water corrodes the metals when used in boilers. Because of the presence of salts, hard water is unsuitable for dyeing, tanning, and for the preparation of chemical reagents. Hard water leaves salt deposits in industrial boilers which may cause explosions. Preparation of distilled water. Distillation is a process by which all the dissolved impurities can be removed from water. In the laboratory, distilled water can be prepared by using a simple distillation apparatus consisting of a round-bottomed flask with a side tube, a thermometer, a Liebig's condenser, a receiver, a stand, wire gauze and a burner. The apparatus is set as shown. When impure water is heated in the round-bottomed flask at 100 degrees centigrade, it begins to boil and becomes steam. The steam passes through the Liebig's condenser where it changes to water. The water that gets collected in the receiver is the distilled water. Atmosphere. Introduction. The earth has 3 parts: land, water and air. The earth is surrounded by a layer of air called atmosphere. The atmosphere is made up of oxygen, nitrogen, carbon dioxide, rare gases like dust and water. The atmosphere provides oxygen, which is essential for life. The atmosphere protects us from harmful effects of ultraviolet radiation. Composition of air. The atmosphere is divided into 5 layers as shown. As we pass through the layers from the outer space to the Earth's surface, the composition of gases change. The Earth's surface is made up of approximately 78% of nitrogen, 20% of oxygen, 1% of noble gases and carbon dioxide, water vapor and pollutants constitute remaining 1%. The composition of gases is shown in the figure. Air as a mixture. A mixture is made up of 2 or 3 constituents. The composition of mixture is not constant and it varies from place to place. In a mixture, the properties of constituents are retained, so also in air. If the constituents are mixed, no energy change or chemical change takes place. The constituents of air and their percentage are shown in the figure. Air pollution. Pollution means making dirty with harmful or poisonous substance. Air is polluted by carbon monoxide, sulfur dioxide, sulfur trioxide, smoke, dust, soot, etc. Effects of air pollutants. The minute solid particles suspended in the air in the form of smoke or dust are called suspended particulate matter, SPM. According to the World Health Organization, WHO, suspended particulate matter or SPM is the most dangerous for public health. It is estimated that about 450,000 deaths take place in the world due to SPM related pollution problem. About 20% these deaths are heart related and 28% are lung related. The smaller particles in SPM are more harmful as they go deep into the lungs and stay embedded there for a long time. Air pollution causes headaches and dizziness, irritates eye, damages to lungs, damage the plants also. Nuclear pollutants cause cancer. Acid rain. The smoke and fumes from burning fossil fuels like coal rise up into the atmosphere, and oxides of certain elements present in the smoke combine with the moisture in the air to form acid rain. Sulfur dioxide and oxides of nitrogen are the main chemicals that create acid rain. These gases are released from power plants and other sources, and the winds blow them far from their source. If the acid chemicals in the air are blown into areas where the weather is wet, the chemicals combine with water to form mild acids. These acids can fall back to earth as rain, snow, fog or mist. In areas where the weather is dry, the acid chemicals may become incorporated into dust or smoke. Sunlight increases the rate of most of these reactions. Acid rain can damage the environment, human health and property. Inert gases. The inert gases are unreactive gases. They are present to an extent of about 1% in the air atmosphere. Some of them are helium, He, neon, Ne, argon, Ar, krypton, Kr, and xenon, Xe. Helium, He, is used in meteorological balloons. It is also used by sea divers. It's used in advertising displays. Neon, Ne, is also used in light for advertising displays. Argon, Ar, is also used in light bulbs. Krypton, Kr, it is used in lighthouse and airport landing lights. Xenon, Xe, it is used in photographers' flash gun. Discovery of hydrogen. Hydrogen is the lightest known element in the universe and is the most abundant of the chemical elements, constituting roughly 75% of the universe's elemental mass. Hydrogen was discovered in the year 1776 by Henry Cavendish. A. L. Lavoisier was the scientist to name it as hydrogen, meaning water producer. Oxygen and oxide. All living organisms on the earth require oxygen and its compounds for various life activities. We cannot exist on this earth without oxygen. Living things need oxygen to respire and exist. All the fuels burned in houses, factories, automobiles and other places consume oxygen. Scheele and Joseph Priestley discovered oxygen independently. Lavoisier coined the name oxygen for the gas discovered by Scheele and Joseph Priestley. Occurrence of oxygen. About half of the mass of the Earth's crust is made up of oxygen in the form of silicates. The atmosphere contains 23% by mass of oxygen, 21% by volume. Around 89% of the mass of the oceans of the world is oxygen. Oxygen is a constituent of water, rocks, minerals, vegetable matter, sand, etc. Laboratory preparation. Potassium chlorate is mixed with 1/12 of its weight of pure manganese dioxide. This mixture is taken in a hard glass test tube. Test tube is closed with a 1-hole cork. Delivery tube is attached to the test tube through the hole in the cork. Other end of the delivery tube passes through the hole in a beehive shelf kept in a water trough. A gas jar filled with water and placed over the beehive shelf. Now, the mixture of potassium chlorate and manganese dioxide is strongly heated. Oxygen gas escapes through the delivery tube and is collected in the gas jar by the downward displacement of water. The gas collected initially contains mostly air. Properties of oxygen. Physical property. Oxygen is colorless. It has no odor. It is slightly soluble in water. It is slightly denser than air. It is not easily converted into the liquid form. Chemical properties. Combustion of non-metals in oxygen. Carbon. A small piece of carbon, charcoal, is taken in a deflagrating spoon. It is heated till red hot. The spoon is lowered into a jar of oxygen. Carbon burns with an orange flame, forming carbon dioxide. C plus O2 is equal to CO2. Sulfur. A small amount of sulfur is placed in a deflagrating spoon. It is heated until it starts burning with a pale blue flame. The spoon is then lowered into a jar of oxygen. Sulfur burns very brightly, forming sulfur dioxide. S plus O2 is equal to SO2. Preparation of CO2. CO2 is conveniently prepared in the laboratory by the action of cold dilute hydrochloric acid on marble, CaCO3. CaCO3 plus 2HCl gives CaCl2 plus H2O plus CO2. Marble chips are placed in a wolf's bottle and then dilute hydrochloric acid is added through the thistle funnel. The carbon dioxide evolved is bubbled through water to free it from acid spray. It may be dried and collected by the upward displacement of air. Physical properties. CO2 is a colorless, odorless and tasteless gas. It is heavier than air. Hence, it can be transferred from one vessel to another as if it were a liquid. CO2 is soluble in water. Aquatic plants and animals grow under water using the dissolved carbon dioxide. CO2 can be liquefied and solidified by applying pressure and cooling. Chemical properties. Acidic nature. Add water to a jar of CO2. Shake well and test the solution with a blue litmus paper. It is acidic to litmus. CO2 plus H2O on reversible reaction. H2CO3, carbonic acid. Burning sodium and potassium continue to burn in CO2. Since these oxides are basic, they immediately combine with more CO2 to form carbonates. 4Na plus CO2 gives 2Na2O plus C. Uses of carbon. CO2 is used in fire extinguishers. It is used in the manufacture of Na2CO3 washing soda and NaHCO3 baking soda. Liquid CO2 is used in sugar industry. Liquid CO2 is used in some refrigerators in place of liquid ammonia. A mixture of oxygen and 5 to 10% CO2 is used for artificial respiration. It is used as dry ice. It is used in the preparation of aerated drinks. Dry ice and its uses. CO2 gas is liquefied under high pressure. This liquid CO2 at minus 57 degrees centigrade is allowed to pass through a small nozzle. Cooling occurs and a part of the liquid CO2 freezes to a white solid that is compacted into cakes. This is called dry ice. Dry ice is used as refrigerant for preserving perishable foods, ice creams, vaccines and vegetables. Ordinary ice melts, but dry ice sublimes into a dense vapor. As it doesn't pass through the liquid state, it is more convenient to use as a freezing agent by ice cream manufacturers.